Good morning, everybody. I hope you guys are doing well today. Today, I woke up this morning and it was like the perfect weather to just like go back to bed. It was raining and dreary and overcast, and I'm like, ugh, my bed is calling my name. But I fought the urge and now I'm here. So we'll talk about three-dimensional Cartesian coordinate system today. Woohoo! The good news with today's lesson is that we've actually already done some of it. We've already looked at three dimensions. I think when we were looking at our vectors, we and the dot product, I think we may have seen some three-dimensional things there already, with an x, y, and z, or v, w, whatever they use, UVWX, I guess. So some of today should be review. And then, well, hopefully most of today is because we're just using existing formulas that we already know and then just expanding those to incorporate that third dimension. Before we start looking at that, though, I do want to go over that one major announcement regarding the April 2nd deadline. So, April 2nd is going to be next week, Monday. So, that's when we're pulling grades for midterms. Now, technically, that is the Monday for spring break, right? And we'll come back on that Tuesday, April 3rd. But you need to be caught up by April 2nd. So any zeros for missing work will turn permanent at that time. I do want you to get everything up to and including 8.03 turned in. Now, technically, at by if you follow the pace of the calendar, we'll be at 8.04 at that time. So I'm actually pushing it back a little bit. Um, so everything up to and including 8.03. If you're on pace with the calendar, you're going to be just fine because you already have 8.03 turned in from last week. So if you're following on pace with the calendar, you have absolutely nothing to worry about. You have no zeros in your grade book. Nothing will turn permanently zero, and you're just kind of moving forward with the scheduled pace. If you are behind, though, you're going to want to make sure that you're getting your missing assignments turned in by that April 2nd deadline, because first thing Tuesday morning, I'll be pulling those grades that you have for your midterm reports. Any questions with that at all? And honestly, the whole purpose behind the midterm grades is to make sure you know where you're at, and you have a plan to finish the year off strong. I would like corrections to be turned in at that time as well. However, correction wise, I'll still accept those if you're going to do them in quarter four, to prepare for your final exam or whatever it may be. So if you feel like you need to do corrections during quarter four for the work that was in quarter three, I'll allow it. Although it'd probably be ideal to do your corrections before you go into a test, right? Just so you know that you can fix those mistakes before you go into your test. But corrections is one thing I will allow to move into quarter four. But as far as the work itself, that's got to be turned in first. So yeah, good question. Any other questions regarding that? Awesome. All right, then we're going to go ahead, and I think this is the last lesson of Unit 8, is it not? Can somebody correct me if I'm wrong? I want to say that this is the last lesson of the unit already. Yeah. So here's the thing. When when we come back, do I have let me see. I do not have a Unit 8 review scheduled for us. So when we come back on that Tuesday, or maybe I do, hold on. I gotta check my planner to see what I actually have scheduled here for next week. Next week is April. All right. Oh, you know what? Next week, Tuesday, I do not have a review scheduled. I actually won't be able to hold class because I have to take my son down to Children's Hospital for an appointment. So next week, Tuesday, we actually won't have a live class. If I look at the calendar, I'll see that because I put that on there already. So that Tuesday we come back. If you want to review for your test, you can. Or if you want to take your test this week, because we should be able to finish 8.04 today with no issues. If you want to take your test before you leave for spring break, you can do that. It's open, it's ready to go. That way, if you're worried about forgetting the information over the couple days that you're off, or you just don't want to take a test that day you come back, you can take the test early if you want. So that's totally up to you. Our spring break is not long enough for you to forget the information though. So at least I don't feel it's long enough for you to forget everything we looked at in Unit 8. So I really don't think it'll be an issue when you come back that you have to take a test that second day. Is it ideal? No, because no one likes taking a test, right? But it's not like there's a huge week-long gap in there where you're not doing anything. So I think it should be okay. All right, so let's go ahead and dive into this last lesson of the unit then. So we are talking about three dimensions. So instead of having an XY Cartesian plane, we have an X, a Y, and a Z. So things do shift around a little bit. Instead of the Y going vertical, our Z is now that axis that goes up and down. The X is the one that goes front to back, and the Y is the one that goes left to right. So we can see that it's kind of split into 8 different regions now instead of just 4. So you got kind of 4 regions on the top and kind of 4 regions on the bottom. So there are 8 octants, they call them, in our three-dimensional system here. Now the origin is still at the center, 0, 0, 0, right? And then you can see how they are distinguishing their points. So our ordered triples, that's what they call our points in the three-dimensional system, our ordered triples, they still go alphabetical order. So it's still X, Y, Z, right? This time X, though, is the moving forward back, Y is left or right, and Z is up or down on their coordinate plane. All right. Any questions with this three-dimensional system at all? So we saw a little bit of it last year in Algebra 2 as well, if you guys remember. We did talk about the X, Y, Z plane a little bit back in Algebra 2. All right, you may be asked to sketch a point. You can use GeoGebra if you'd like to sketch a point, but I believe that you may have to switch the window that you're in. So if you're using GeoGebra to sketch a point, I think there's a three-dimensional toolbar or little tab or button or something in the program that you have to click off on the right-hand side, if I'm remembering correctly. So just make sure you're working in that correct view if you need to graph anything. We can also graph the things by hand as well, so if you want to sketch it out, we can graph it that way as well. So looking at the point here, we're going to sketch a point 2, 3, 5. So that means you have to move 2 forward first because that's your X value there. Then we have to move 3 to the right, so technically out here, and then we have to move 5 up. And then we find that ending point. So you can see that three-dimensional trail there, and if you kind of visualize that three-dimensional popping there, we can see that it's going to be higher up out here in this plane or this octant that we have kind of right in front of us. So it's just hanging out up here. They give you a lot of extra planes and everything. Basically what they're just doing with these three planes is showing you that intersection point, right? So they're taking that plane of x equals 2, they're taking the plane of y equals 3 in blue, and they're taking that plane of z equals 5 in this light orange, and they're showing you where they intersect. So essentially that's what's happening, is these three planes are intersecting each other to form that point. Questions with the three-dimensional graphing? All right, here's where the fun stuff comes in. So now we're going to kind of manipulate the formulas we already know for 2 dimensions and expand that to include our third dimension now. So the first two formulas we're going to look at is the distance formula and the midpoint formula. So the distance formula, remember, that allows us to take any two distinct points and find the distance between them. So we can do that in our 3 dimensions as well. Notice everything is the same for x and y. We're just going to add on that third component for the z's as well underneath our square root sign here. And same thing with your midpoint formula. Notice that if it were just 2 dimensions, x and y, that is the same. We're just going to do it again and incorporate the z values of the points. So averaging those z values to help you find the midpoint there. Okay, so nothing too spectacular. We're just kind of repeating the pattern that we see in those formulas to include that third dimension. So let's go ahead and do example 2 on the board here. It says find the distance between the points and find the midpoint between those 2 points. So let's start with the distance formula. We're going to go ahead and take the square root of the x's subtracted there. So -2 minus 4 and squared. We'll do the same thing with the y's, 3 minus -1. Careful of those double negatives when we're working through this. And then 1 minus 5 for the z's. All right, let's see what we get here. This will be a -6 squared. And while I'm typing this out on the board, why don't you guys go ahead and use your calculators and let me know what we're going to get after we square each thing and add the components together. So why don't you guys work ahead of me and actually perform the exponents and addition piece of the formula here. What are we going to get underneath that square root sign? So 36 plus 16 plus 16, what does that equal? A 68. Okay. Now we can go ahead and try to simplify the square root of 68. We can turn that into a decimal, or we can leave it as a radical. What's the decimal answer of the square root 68? Approximately the decimal answer. About 8.25. Thanks, Rachel. That seems right because 64 would be your 8. So a little bit higher than that should incorporate your 68. Good. And then if you want to simplify that to leave it as a radical, you're going to try to find a perfect square that's a factor of 68. So 4 times 17 gives you that. So it looks like that would simplify to a 2 times square root of 17 if we want to leave it as a radical. Good. Let's go ahead now and find the midpoint of those. So the midpoint now is when we add the x's together, divide by 2, add the y's together, divide by 2, and add the z's together and divide by 2. So really basic algebra here. Go ahead and simplify those for me, and what are we going to get for the midpoint? One, 1, 3. Yeah, so it's nothing like overly complicated by any means when we're working in our three-dimensional system. We're just expanding the formulas that we already know. Questions with the distance formula and the midpoint formula? Fingers crossed things remain like this, right? Because this isn't bad at all. All right, the next thing we're going to talk about is the equation of a sphere. So if we go back to our geometry days, we definitely explore like the volume of a sphere and maybe the circumference and the area, but we never really explored the equation of a sphere. Right, so a three-dimensional object is, or a sphere classifies as your three-dimensional object. So we need that x, y, and z for the equation of it. So even though we do explore the volume and the area and everything else for a sphere back in geometry days, we can't really explore how to write the equation until we get here and understand our three-dimensional system. So this should remind you of a circle, right? The x and the y piece of it, where you have h comma k, that's your center. So these first two pieces should remind you of the equation of a circle. To incorporate that three-dimensional piece, we now have to include the z aspect of it. So instead of having a center that is at point hk, our center is now located at point hkl. Right? R is still determining the radius of the sphere though. So we're still using an r squared after the equal sign. All right, let's go ahead and write our standard equation of a sphere if it is centered at 2, 0, negative 3 and has a radius of 7. So what is the equation of our sphere going to look like for this setup? I see Isaias typing there, so I'm going to start the equation here on the board and then just fill it in once I see his response come through. I love the emoticons. So x minus 2. Good. And Rachel's also typing. So keep going, Rachel. We'll make sure that you seconded Isaias's result here. Let's see. The 0. Is this going to just be a y squared? Yeah. So y minus 0. So technically, if you have a minus 0 in here, you don't need to write that. You can just leave that as your y. So I'm not sure which emoticon was our thumbs up. Must have been our y maybe inside our parentheses there, huh? And then at the end we'll have z plus 3. And we'll equal 7 squared, or if you want to simplify the 7 squared, we can write that as our 49. Good. Now you can leave the minus 0 in here. There's no harm in that. Just note that it can also simplify to just a y inside that middle parentheses. Awesome. So again, not too bad. We just use substitution into that equation, and we can relate that back to our equation of a circle. We just got to add that third component for the 3D aspect. All right, so let's go ahead and sketch the graph of this three-dimensional plane here in space. So they give us that every plane can be written as that formula here. And they do include the constant on this side, but I like to move the constant over, because if we can move it over, we can find the intercepts of each axis, right? If it's in the standard form, what we did back in Algebra 1 is we used that linear equation to help us find the intercepts. And once we had the intercepts, we went and graphed those, and we just connected them with our line. We're going to use that same approach here, only instead of having a line as our final answer, we're going to have a plane that represents our final answer. Right? So to sketch the graph, it's going to look like a plane instead of a line. But I still want to use the intercept form to help me find those x, y, and z values. So if this were just in standard form and we had something like 12x plus 15y equals 60, what would you do to find the x and y intercept? So without putting it into slope-intercept form, what would we do with that equation without rearranging it at all to find the x and y intercept? Plug in 0 for the other variables, right? I like to call it the cover-up method as well. So plugging 0 in kind of makes that variable disappear, right? So if I were to plug 0 in for y, that disappears. I can cover it up, and I can then solve for the x that's left. What would be the x-intercept of that graph? So what's the x-intercept for that graph? 5, right? Because 60 divided by 12 is 5. So technically, I can go ahead and still use that for my x-intercept in this three-dimensional system as well. Let's find the y value. So using the cover-up method, we would cover up the x's there and solve for the y. What would the y be? 4. All right. And now we're just going to do the same thing with the z as well. So we'll cover up the x and y and then solve for z. Yeah. All right, now to graph it, here comes the fun part. So hang in there with me because it's a little bit hard to graph a three-dimensional system in a two-dimensional board here. Okay, this is going to be my best representation here. So this is the x-axis, the one that's kind of coming out at us. Here is the y, and here is the z. All right, so for the x coordinate, should I move 5 to the front or 5 to the back? Five to the front. All right, and no pressure here to compare this to the GeoGebra program, right? All right, so far we're good. So the y-intercept, so I move to the right or to the left on the y-axis to find that y-intercept. One, two, three, four, to the right. And then should I move 3 up or 3 down to get to the z? Yep. All right, so what this looks like then, if I were to connect them, and hopefully in GeoGebra it looks somewhat similar, is you should have an intersecting feature there of those 3 planes that looks kind of like a triangle. So this right in here is going to be the graph of this equation. So instead of having just a line, we do have a plane as our graph in the three-dimensional system. Okay, and Isaias, you can confirm in GeoGebra that's kind of what it looked like. Maybe there are more colors involved or whatnot, but the intersection of that kind of looks like that triangular piece. Okay. Yeah, so again, this is kind of the best representation that I can do on a two-dimensional board, right? So the GeoGebra program probably is going to be a little bit more accurate, but it's going to look something like that. All right, any questions with how we sketched that by hand? So if you run into a graphing question on your homework assignment, you can use GeoGebra to assist you, or you can just kind of sketch it by hand as well, like I did here, and just do the best you can to your ability. Obviously, we're not perfect, myself included. I'm far from perfect. So as long as we're close to it, that's what I'm kind of going for. All right, we want to extend our three dimensionals into our vector relationships in space. We kind of already looked at this. So this is nothing new for you. Hopefully you don't need to add this part to your notes. But again, just notice that when we're doing addition, we add those third z terms together. Same thing with subtraction. The magnitude, you're just squaring that third term. We looked at the dot product, I believe, already of three-dimensional vectors. And then your unit vector is kind of performed the exact same way, but you're using that magnitude of v from up above, right? So that's how we would use or find the magnitude of that three-dimensional vector. What we probably haven't looked at yet is the equations for a line in space. So the vector form of creating a line in space is by taking your point. So if L is a line through the point here in the direction of a non-zero vector, V, then your point P is on line L if and only if we follow these formats here. So R0 is technically that point that you started with, right? So that would be our x, y, z plus t times vector v. Now sometimes we have to find this vector v by using our head minus tail rule. So if we're given 2 points, we might actually have to put it in our vector form before we get the actual vector there of a, b, and c. Now, once we have it in the vector form here, we can easily go ahead and transform that to our parametric form by taking the value from the first vector and adding it to the value of the second. So down here, if we take a look at example 7, this sounds a lot more complicated than it actually is. It's actually pretty basic. So if we have a point here, and it's going in the direction of vector v, then we can write the vector form using that point, 4, 3, negative 1, plus t times the vector that it's going in, that direction there. Okay, we can then take this form and create equations for that parametric form. So to create the equations, we do r plus t times negative 2. So that's where the 4 minus 2t comes into. For the y value, we'll do 3 plus t times 2. So that's where they get this equation right here. And the last one, they're just doing it with the negative 1, and they're distributing that t to get that third equation for z. So it's really not that difficult at all, as long as we know that we have to use the distributive property for that t, and then we're just kind of matching the terms up for the equations there. We're going to go ahead and take a look at an example though, because what if they don't give us vector v? Can we find that vector v so that I can put it in this vector form and then translate that to the parametric form? So that's what we're going to take a look at now. Okay, so to put it in the vector form, if we're given 2 points, so if we're given 2 points, we have to find the vector component of that by doing the head minus tail rule. So I have point A, B. We've got to do -1 minus 3, right? So that head minus tail rule is you take that second value and subtract off the first. And we're going to do that for each set of terms, right? So 2 minus 0 and -5 minus a -2. Let's go ahead and simplify that. What do we get for this vector v then? A -4, +2, and a -3. All right, so here's that vector v. So now to put this in the vector form, we're going to go ahead and take your initial point, and the initial point is what we start with, right? That's the head value there. So we're going to take that point and add it to the t times the direction of our vector now. So the -4, the 2, and the -3. So all we essentially did was mimic the step that we had back here, right? There's that initial point plus t, and we found that vector v. So that's how we got this form right here. This is the vector form, okay? Let's put that into the parametric form. So essentially, we've got to create equations for x, y, and z. Let's start with the x. What equation can we create from this vector form for x? We'll get x equals what? Yeah, 3 minus 4t. Beautiful. So don't forget we are distributing the t through that vector v here in order to come up with our equations, but then we're just kind of grouping those terms together. So the 3 has got to go with the -4t. What about the equation for y? What equation can we get for y? Yeah, just a 0 plus 2t, which is a 2t. And then what equation can we create for z? Yeah, and I'll just color code these. So -2 plus -3t, that's just a -2 minus a 3t. So now we got that parametric form for our equations. And the parametric form, remember, has that t in it. So there we go. Questions with how we created the equations there in the parametric form, or how we got our values for the vector form. So any questions with that at all? All right, let's go ahead and practice, practice, practice. All right, so let's take a look here. I'll get the polling going. This is going to take me a moment to change our polling features here. Okay, so instead of the check and X, I now have our polling options up there, and I also made them so you can't see each other's response. So make sure you answer this to your best ability. It says choose the correct answer below. It says plot the point whose coordinates are -3, 2, 0. So which one has the best graph here for this point? Is it the point right here in choice A? Is it the point down here in choice B? Is it the point out here in choice C? Or right here in choice D? So which one of those represents the point -3, 2, 0? So go ahead, use your polling options. I see Isaias and Rachel are already logged in. We're just waiting for Callie, Charter, and Rebecca. And if you're not sure, make your best educated guess. Yep, so if you go up where like the raise your hand tool is, above your name in the participant list, your check or red X selection that used to be there is now an A with a box. So if you click on the arrow next to that A in that box there, it'll give you more options to choose either A, B, C, or D. Can you see that little tool up there? Okay, awesome. Okay, once Rebecca locks in, I'll go ahead and publish the results on the board. Yeah, if you want to change your response, you can do that in the meantime, but I'll publish them in just a moment here. All right, there we go. We're all locked in. I'm the only one that's not. So when you see that 1 out of 6 for not, that's me. All right, so A is the most popular choice there, and then B and C, but D did not receive any responses. Yeah, so -3 means we're moving back on that x-axis first. So we need to move back, and only 2 choices do that, A and B. So C and D are out because we need to move backwards on the x-axis. The next thing we need to do is move 2 to the right on the y. And so far both points have done that in A and B. The third option is, or the third point there is 0. So technically once we move 2 to the right, we don't need to move up or down anywhere. And that's where choice B is going to fail, because technically choice B looks like it just goes 3 to the back and 5 down. So that one gets thrown out. We do want to go with choice A. So if you said choice A, you are correct. Nice job. All right, the next one, we're not going to use polling. We'll just work through it as a class here. It says calculate the expression using R as this vector and V as this one. So let's just add the 2 vectors together. What do we get when we do R plus V? If we can do our simple addition, we can definitely handle this one because we're just adding our like terms together. So what do we get for this resulting vector when we do R plus V? If I have enough room. Ooh, yeah, we got our heart going. We should have a -3 there, 5. Oh, nope, that is a +3. My bad. Yep, so heart's correct. So 3, 7, -6. Awesome job. All right, let's go ahead and do our order of operations with the vectors down here. Notice we do have to do order of operations correctly, so you must be adding before you're multiplying there. So, and technically this I don't know if we can multiply vectors together. I believe that's going to be the dot product, actually. That's what the little marking circle is, because we can't multiply vectors unless it's just a scalar multiplication. So that dot actually means the dot product. But before we get there, we've got to do v plus w. What is v plus w? So let's see here. Negative 3 plus 4. Sorry. All right, sorry about that. Negative 3 plus 4 should be a positive 1. 3 plus 2 is a 5. And negative 5 plus negative 4, negative 9. Thanks. All right, so now we have the dot product that we have to do between these two vectors. So remember, the dot product is when we multiply those terms together and then find the sum of all of them. So we'll start with negative 2 times 1. And then we'll do those second components, 1 times 5. And then 5 times negative 9. Thanks, Isaias, to just confirm that. And when we add those together, what do we get? Is that a negative 42 if I did that in my head correctly? Awesome. So I don't think that the operations themselves were the confusing part. It was knowing that the dot product needed to be occurring there, that instead of the multiplication piece, that's what the little dot represented. Questions with our vectors at all? All right, we're back to our polling tools here, and we'll probably finish with this one, which is fine. It says write the vector and parametric forms of the line through the point P0 in the direction of vector v. So good news here is they gave us the vector. We don't need to find that using 2 points. So they already did the hard work for us, if you can call it hard work there. But which one of these is the correct setup for the vector form if this is the point and this is our vector? So is it choice A, B, C, or D? Which one of these is the correct vector form of the line? So go ahead, use your poll. Oh, I was talking before the mic jumped on there. Go ahead, use your polling tools to select the best choice. Okay, we're just waiting for 2 more people to lock in, 1 more person to lock in. All right. Woohoo! Oh, everybody said choice B. Yay! Choice B is correct because we want to start with that point and we are multiplying t through the vector. All right, if this is the correct vector form, which choice below is the correct parametric form for what we just established up here for the vector form? Sorry. So you use those polling features again now. Which one of those is the correct parametric form? right, we're waiting for just 2 more responses to be locked in, and then I'll publish the results. Just 1 more response. All right, let's see where we're at. This time we differ a little bit, but majority vote is D. And D is going to be the correct answer there because when I take a look, remember we're matching up the components here. So the first one is going to be x equals 1 plus 7t. So 1 plus 7t, really the only option that has that would be choice D. And let's just verify that the rest of them would be correct. So y would equal negative 2 plus 9t. So negative 2 plus 9t, good. And then the last one would be 4, z equals 4 minus 6t. Good. So D is that correct choice there. Any questions with how we went from the vector form to choice D for the parametric form? Okay, we're going to wrap up there then for the day. The only thing we didn't get to was just looking for the distance and the midpoint, which really you guys can handle using those formulas like we saw in example 1 of the class today. All right, you should be all set for 8.04. Because we did finish that today, Thursday's class is going to be a work day. So you guys can come in. I'm still expecting you to come in the morning, but it probably will be a very shortened class if there aren't any questions regarding 8.04. All right, so heads up, Thursday is going to be a work day for you guys. All right, if you guys don't have any questions, I'll let you go. Have a great rest of your Tuesday, and I'll see you Thursday morning again. Bye, everyone.